Hello and welcome to section 7.1 of our linear algebra notes. Today we're going to talk about diagonalizing symmetric matrices and sort of why the symmetric matrices are interesting in their diagonalization, and then we'll also construct the spectral decomposition of a symmetric matrix. So a symmetric matrix is a matrix that equals its transpose. We've seen these before. One example would be the matrix if we put something like this. And so you see, if you reflect along the main diagonal, you'll get back exactly what you started with. And our first quiz question asks, is it possible for a 2x3 matrix to be transposed and equal itself? Okay, so now let's look at a special matrix B. So notice this matrix itself is actually a symmetric matrix. We've written down its diagonalization, and let's go ahead and use that to list the eigenvalues. So this is the type of thing that's nice about diagonalization. We have 1, 3, and 7 are our eigenvalues, all with multiplicity 1. And we can do a basis for our eigenspace for each of those just by looking at our P matrix. So the first column of P corresponds to the eigenvalue 1. And so we get the basis 1, -1, 1. And then the eigenvalue 3 is the second in D, so it's the second column of P. And then the eigenspace corresponding to eigenvalue 7 has basis, the third vector of P, which is 1, 2, 1. And now our second quiz question asks us to pick two eigenvectors from different eigenspaces. So you could pick these two, you could pick these two, any of them, and compute their dot product and see what you get. Okay, let's look at a matrix that is not symmetric. So here, C transpose does not equal C. And let's do the same thing. So here we have an eigenvalue 5, which has multiplicity 2, and an eigenvalue 4, which has multiplicity 1. So for these then, for the eigenspace corresponding to lambda equals 5, we take the first two vectors of P, and then for the eigenspace corresponding to lambda equals 4, we take that last vector. And now if we take eigenvectors from different eigenspaces, like let's take, for example, -2, 0, 1, and we compute the dot product of that with a vector from the eigenspace for lambda equals 4, you'll notice that what we get is -2 times -1 plus 0 times 2 plus 1 times 0, which just equals 2, which is not 0. So these are not orthogonal. So our eigenvectors are not orthogonal. And if you remember, if you got your quiz right, when you did the one where the matrix was symmetric, you actually got that if you picked two eigenvectors from different eigenspaces, their dot products was 0, so they were orthogonal. And in fact, it turns out that anytime a matrix is symmetric, then eigenvectors from different eigenspaces are orthogonal. And in fact, a matrix is orthogonally diagonalizable, and so that means that our matrix P is an orthogonal matrix, which means that the dot product of the columns is 0, and the columns are unit vectors. So we have unit vector columns, and the columns are orthogonal. This happens if and only if A is symmetric. Well, let's look at that. So if we have, let's look at one way. Let's say A is orthogonally diagonalizable. So that means instead of P inverse, we can go ahead and write P transpose. Well then, if we take the transpose of A, we can take the transpose of P dP transpose, which remember, when we do transposes, kind of like the inverses, you take the transpose of each individual matrix, but you flip the order of them. And when you take the transpose of the transpose, you get back what you started, and the transpose of a diagonal matrix is itself. And so, in fact, you get back A. Okay, so we can use this to orthogonally diagonalize the matrix that's given here. And so what I'm going to do is, you can go ahead and practice your computing bases for eigenspaces. To save on time, I'm going to go ahead and just write down when lambda equals 3, when you do your computations, you get a basis of -1, 1, 0, and 1/2, 0, 1. Now, unfortunately, if we want, okay, first of all, you see this is symmetric, so that's good. So we know that if we have eigenvectors from different eigenspaces, they're already orthogonal. But if you look at these two vectors, and let's just go ahead and call them v1 and v2, they're not orthogonal. So, and we need to have our P have orthogonal columns, so we also need the vectors in the same eigenspace, the two linearly independent vectors from the same eigenspace, to be orthogonal. So to make an orthogonal basis, and we're also going to need it to be unit vectors. What we're going to do is we're going to project the second vector onto the first. So we're using the tools from chapter 6, and then use the orthogonal component. So remember, let me write this down. Okay. So remember that we can write V2 as the projection of V2 onto V1 plus a new vector, we'll call it Z2, and that new vector Z2 is orthogonal to V1. So we have, remember, this is using the fact that we can take our vector V and break it down into something that lies along V2 and something orthogonal to, lies along V1 and something orthogonal to V1. And then this right here is what we'll use. And so we need, so that Z2 is what we want, and that's going to equal V2 minus, and then let's go ahead and write down the formula for this projection. So if you recall, we do the dot product of V2 and V1 over the dot product of V1 with itself, and then times our vector V1. And so when we plug everything in, we get our V2 minus. And again, the reason I have this V2 minus is because up here I had V2 equals the projection plus Z2. And so over here I solved for Z2. Okay, so we do our dot product of V2 dot V1. We get, I believe, -1/2 over, and then V1 dot V1 is 2. And all of that times V1 And so that ends up being 1/2, 0, 1 plus a fourth times this vector. And we add this all together. 1/2 minus a fourth equals a fourth. And now you can test this if you take this new vector, this z2, and you dot it with v1, you will see that you do get 0. So these vectors are orthogonal, but we still need them to be unit vectors. And so in order to get unit vectors, we need to do what's called normalizing, which is where we divide by the length of the vector. So first we take v1 and we divide by its length, which is the square root of the dot product of it with itself. And that's going to end up giving us negative 1 over root 2, 1 over root 2, and 0. Now this is a unit vector, and we do the same thing for the z2 vector. So we multiply that by 1 over, when all is said and done, you should get the square root of 18/16. And so that's going to end up being, let's see, that's square root of 18 over 4, so 4 over root 18. So I believe this is 1 over root 18, 1 over root 18, and let's see, 4 over root 18. Yeah, because when you square it, you get 16 over 18 plus 1 over 18 plus 1 over 18. Okay, good. So that was one of our unit vectors. And then we need to also deal with the eigenvalue lambda equals 15. And again, you can pause this, find a basis for this eigenspace. You should get -2, -2, 1. And you'll see that will be orthogonal to both of the vectors, both of these unit vectors from our other space. And again, we need to normalize. And so we take this vector and divide by its length, and that is the square root of 9. And so we get, which is 1 over 3. So we get -2/3, -2/3, 1/3. And so now we're ready to write down our P and our D. And so we take each of our vectors. So our first vector, so this is now a unit vector in our eigenspace -3. And then our second unit vector in our eigenspace for -3, which now is orthogonal to the first vector. So that was this one. And then we also have our eigenvector that's guaranteed to be orthogonal to the other two because our original matrix was symmetric. And then we also need to write down our D, which, let's see, we had the first two vectors corresponded to -3, and then the last one corresponded to the eigenvalue 15. And so now we have orthogonally diagonalized that matrix. And you see that P is a nice matrix. Okay, so the last thing that I want to talk about is the spectral theorem. And this is just listing some properties about a symmetric matrix. So first of all, it has all real eigenvalues. So it doesn't have any complex eigenvalues as long as you count the multiplicities. And the dimension of the eigenspace equals the multiplicity. So these are always diagonalizable. And I guess I can go ahead and say further, we have that it's orthogonally diagonalizable. And then the eigenspaces are mutually orthogonal, meaning that eigenvectors from different eigenvalues are orthogonal themselves. And let's see, so now we have something called, so we can use this to write down what's called the spectral decomposition. And basically what we're doing here is we're writing A as a sum of symmetric matrices that are multiplied by our eigenvalues. So if A is in fact a symmetric matrix itself, then we can write it as PDP transpose. And if we write down P as the column vectors U1 through UN, D, where we list out our eigenvalues, which we know exist from our spectral theorem, and then P transpose, we write down those eigenvectors as rows instead of columns. Well, if you think about what happens when you're multiplying matrix times a vector and then the other vectors to make the columns, what you're really doing is this first column of your diagonal matrix is pulling out lambda 1 times u1. Then our second column will pull out lambda 2 times u2, and so on. So that first product is going to look like lambda 1 u1 up through lambda n un. So these aren't added together, these are columns. And then each of those are multiplied by the transposes. And so what you end up with is exactly what we were looking for, where we have U1 transpose. And note, this is not the dot product because the transpose is on the right. It's UN transpose. If it were the dot product here, it would be UN transpose times U. And so this is called the spectral decomposition because the spectrum is the set of all eigenvalues of A. So we're kind of breaking A down into a sum of smaller pieces. So this is again a way to sort of see our eigenvalues, and we kind of see our eigenvectors as well in this. So let's go ahead and look at this particular example. So we have 6, -2, -2, 9, and the spectral theorem tells us that you can be written as our first eigenvalue times our first eigenvector times our first eigenvector transpose, and then our second eigenvalue times our second eigenvector times our second eigenvector transpose. And so we can write that down, and we get 2√5, 1√5. So 5 is our eigenvalue times 2√5, 1√5 times the transpose, 2/√5, 1/√5, and then plus 10 times our second eigenvector, -1/√5, 2/√5, and then -1/√5, 2/√5. And if you multiply this out, again, good time to practice your matrix multiplication, so you can pause it if you'd like. And we end up with these symmetric matrices multiplied by their eigenvalues. And if you want to further simplify it, you get, in this case, 4, 2, 2, 1 plus 2, -4, -4, and 4 times 2 is 8. So this is the spectral decomposition, and if you add those up, you'll see that you do, in fact, get the matrix we wanted. Now we'll stop there.